next presenter already on stage, Dan Grois from Comcast, talking on deep neural networks for video coding.
Okay, so hello everybody. We are going to talk about an exciting topic today, neural networks. Before I start, I would like to understand how many of you actually are familiar with neural networks. This is considered to be a very hot topic today, great. And how many of you are actually using neural network in the workflow? Great, at least some people here. So if we are looking forward, let's say 3 to 5 years, I would expect most of you raising your hands because this situation is going to be changed and we'll see now how exactly. Okay, so let's start. I will start my talk with the introduction into deep neural network, followed by actually explanation how deep neural network can benefit video coding process. Finally, we'll provide an overview and future perspective in this regards, okay? So introduction to deep neural networks. People started actually to be curious about how our brain works already some time ago. Okay, and if you look at this cover of this journal from 1848, you can see that already in this time, which is something like almost 200 years ago, people started to ask questions. Okay, here you see drawings from 1899, also somehow representing neural networks. So, how, in your opinion, neural networks works? Somebody have an idea how actually neurons communicate each other inside our brain? Anybody? You raise your hand. Any ideas? Okay. So, did you know that our brain contains something between 80 billions to 100 billions of neurons? Did you know that? So, how actually our neurons communicate? Because it's a lot of neurons, okay? So here's an answer. Let's take a look at the picture of a neuron. This is a biological neuron. It has a cell body here. My pen is not drawing. Okay. It has a cell body in the middle. It has an axon. This is a long tail which you can see on the right side of the neuron. It has a dendrites, which actually represents this structure. I tried to draw. Okay, so this is the cell body. This is the dendrites. They're also located here. And this is an axon. This is actually an extension of the cell body. Now, what is interesting to note that neurons inside our brain are not physically connected. Okay? So what does it mean? If they are not physically connected, how actually it's possible to transfer information from one neuron to another one? It's quite interesting, right? So when actually one neuron would like to transfer the message to another one, it sends an electrical signal. This electrical signal starts from here, and it goes along the axon towards the dendrites, which are located here. And then the signal comes to this gap, okay? So all this junction, which includes a part of the first neuron and the second neuron, including the gap, is called synapse. So, something like that. So what actually happens, the electrical signal reaches this point and it causes release of chemicals. Okay, it causes release of chemicals. And these chemicals which are released from this point, they actually reach the second neuron and they trigger the electrical signal on the other side of the synapse, so it's another neuron. So we can summarize that neurons communicate by both sending electrical signals and chemicals, okay? So this is quite complicated communication. And think that we have something like 80 to 100 billions of neurons in our head, and all this should be synchronized, which is quite amazing. Here you can see, works, just a second. No. Just should work. Okay. So here you can see some kind of simulation how signals are passing from one neuron to another one. And at this point, you can see that signal reaches this synapse that we have been talking about. And it triggers, it actually causes release of chemicals at this point. Chemicals are absorbed by the second end of the synapse, and they trigger electrical signals. Okay. What is interesting to note that if this process between some particular neurons happens more often, this connection becomes stronger. Okay. What does it mean? It means that the signal which comes to this junction
has more chances to trigger a signal at the second neuron, okay? At some point, it can happen that actually no signal will be triggered at all, okay? So these connections can be stronger or weaker. And by such a way, actually, our brain can route more important messages and less important messages. And this process is very dynamic. Okay? So until now, I hope it was clear. This is a biological aspect of neural networks. And let's take a look at this smart guy, whose name is Frank Rosenblatt, who in 1957 invented so-called Perceptron. Okay, what is Perceptron? It's actually artificial neuron. And Perceptron, by definition, is an algorithm of supervised learning for binary classified, very simple classifiers, and which actually function that can decide whether yes or not some input belongs to a specific class, okay? So generally, Perceptron allows to decide and divide input signal into yes or no. Very simple, okay? So let's take a look. Here you can see a representation of artificial neuron versus the biological neuron. As you can see visually, already there are quite many similarities, right? So we have here, let's try to draw again. This is not a touch screen, so here you see the cell body, okay? Also here, inputs are provided from this direction, okay? Input signal from other neurons. Similarly, as you can see here, the symbols of X, X0, X1, X2. In artificial neuron, we also have weights. As I said, in biological neural, the weights actually symbolize the strength of connection between two neurons. If the communication between neurons happens more often, the connection becomes stronger. Similarly, in an artificial neuron, this weight can have larger value, okay? So the cell body, what actually it does is summarizes the multiplication of inputs with weights and add an additional bias. Bias in artificial neuron actually determines what are the chances of this neuron to transfer the signal further to other neurons. And also we have here a so-called activation function, which actually introduce nonlinearities in the whole process. If you look at the biological neuron, the process is nonlinear. So we need to introduce nonlinearities here as well, and this is what activation function does. Okay, and we get an output from this part, and similarly here we have here's an axon. Axon just allows to connect to other neurons, and this is terminals which via synapse actually communicate with other neurons. This is a first machine that was designed some time ago, and it was used for image recognition. It has actually many photocells. It was quite primitive, big, and weight actually have been encoded in potentiometer, which have been updated by electrical motors. So as you can see, this is quite primitive system, which have been implemented quite a long time ago. So if we take a look, let's take a look what actually this Perceptron does. So on the left side, you can see a schematic diagram of Perceptron. When you actually activate it, you need to initialize the weights and thresholds. Thresholds actually define your error rate, and the weight actually define, initially it's just zero, some small value, but at the bottom line, at the end, they will show how strong the connection is between input and output. And our target here to get an output as close as possible to the desired output. We are speaking here about supervised learning, so we know what we are going to get, what we are actually aiming to get at the end, yeah? What is the desired output. And we dynamically update the weight and the bias in order to get this output as close as possible to the desired one. Okay, so this is a very dynamic process. And here, for example, you see a very simple classification between the object recognition of dogs and cats. So this line is actually translated and rotated to different directions in order to get best match, to get the output which is as close as possible to the desired output with the predefined error rate, so with the predefined threshold. So this is quite a simple process. And this Perceptron also called a single layer Perceptron because we just have single layer here. Now, the problem with this approach was actually that this perceptron, the single layer perceptrons, could not be trained to recognize many classes and patterns. So all this is not practical, okay? And as a result, the whole research related to that was, let's say so, stuck for quite many years until at some point it was realized that the feed-forward neural network with two more layers, not just with a single layer, can actually provide much better, much greater processing power. So here you can see an example of this neural network. which is also called a deep neural network. It contains more than a single hidden layer, okay? In Perceptron, we just had an input and output, so here we have first layer, second layer, for example, and third layer, and this network is also called a multi-layer perceptron or deep neural network, okay? We have also a shallow neural network. We will not talk about this today, but a shallow neural network, which is not deep, yeah, it's only generally contains just a single layer, maximum 2 layers. Now, here you can see some kind of simulation of the training process. So here you see 3 layers containing, the first 2 contain 8 neurons, the third one contains 2 neurons, and what we're actually aiming to get here is to get an output as close as possible to the desired output. We are talking here about the supervised learning, okay? Now, there are a lot of different variation of neural networks, so-called neural network zoo. Each neural network can be used for each specific case. Generally, normally we don't use all of them. One of the most common and popular is a fully connected network, where all neurons are connected, and convolutional neural networks, where the weights are presented as a 2-dimensional matrix, and we have a convolutional layer by performing convolution, okay? So by such a way we design, we actually define values of neurons, and many of this, what you can see here, are less practical, but you should understand that we have really overall a lot of different variations, and they can be used for different use cases. Now, the interesting question is what actually contain each layer, right? Because let's say we have 3 layers, so what? Yeah, what actually is represented by each layer? So here you can see a very nice visual representation what actually the neurons of this layer contain. Okay, so this is the upper row is actually the second layer, and this is the third layer. The first layer is not shown, but generally the first layer just contains edges and lines, some kind of simple data. The second layer will contain already some kind of shapes. The next one will contain part of object, and at the bottom line, at the final stage, we would like to get a full representation of what we are going to recognize, okay? So if we are going to recognize face, we will get a face. If we are going to recognize the cars, we'll get a car. And so final decision will be just one object, and hopefully we will recognize this object in a correct manner. Now, what is interesting to note that this is very similar to how our visual system works. Okay, we get input from our eyes. The input goes to the back part of our head, to a region called V1. This region transfers information further, and each region actually adds additional information until the final stage of recognition here. Okay, it's very similar. But I would like to notice that still many things are not clear. For example, we cannot point to some specific neuron in some particular layer and say this neuron in this layer shows exactly this representation. And this is an issue. So many neurons actually function as black boxes. Why it's an issue? For example, if you implement this in autonomous cars, and accident happens actually, how we can actually prove what went wrong, yeah? Because we don't really know how it works. So there are still many things that should be discovered and understood before we can say that we really understand how it works. Okay? We are still not there. But what is interesting to note, if you could look here, you see here an error rate. And at this point, which happens several years ago, the neural network accuracy actually became better than human accuracy of recognition. Okay, so at this point, neural network were able to recognize object in a better way than we do, and this is very impressive. Okay, of course it comes with a lot of complexity. So here you can see how many gig operations per second are required, and of course there are a lot of layers. For example, this one requires more than 100 layers, something 150. This is 200 layers, so on. Okay, so we are short in time, so let's go and see how actually deep neural network can be used for video coding. Okay, as you can see here, we have well-known video coding standards and codecs. We have MPEG-2 video, we have AVC, HEVC, VVC, which is currently under development. And during the last, actually, 25 years, we were able to decrease significantly the bit rate. For example, this is a presentation for, on the left side, for full HD. And of course, this came with quite a lot of complexity. And this is the presentation which shows the bitrate reduction for the same video quality. So this was a great work, come with additional complexity, and we're trying to understand now how we can deploy the neural network with some kind of reasonable increase in complexity, because there is an increase in complexity, and there is a huge increase in complexity. And some particular implementations, the decoder size complexity can be increased thousands of times. Okay, so just understand what I'm talking about. Now, let's take a look at the well-known HEVC coding loop. So how many of you attending this workshop last year? I just want to understand how many. Okay, great, nice presentation. So I don't have time to get into details of each tool here, but I just want to emphasize that almost every box that you see here can benefit from the deployment of neural networks. So of course it will come with some additional complexity increase, but we can actually implement it in intra-picture prediction, inter-picture prediction, encoder control, transform, entropy coding, etc., etc., etc. And we will be using the real data for that. And this is one of the big advantages. Standards are based on algorithms and approximations, formulas, okay? And neural networks is based on real data. And this is one of the huge benefits of implementing and deploying the neural network. So this is a summary of various tools. So let's take a brief look at different tools and let's see how they can benefit from deployment of neural network. Inter-picture prediction allows to predict between coding blocks within the same picture. In HEVC we have 35 modes. So in HEVC actually we need to select the best mode out of 35. And how we do this actually, we need to minimize the cost function, okay, for that. And how we can benefit from, introducing neural networks, okay? We can actually learn end-to-end mapping of reconstructed reference pixel to the current block pixels. We are not limited to some particular reference pixels. We are, for example, not limited to the upper and left row of pixels used as references, yeah, right? So we can use allocated structured data for that. And this is really amazing, right? And as a result, we can get gain currently up to something like 11% compared to HM, which is very impressive, I would say, okay? So this is a great benefit of neural networks, that we use real data. And what is more important is the data itself and not the model, okay? Of course, both of them are important, but if you have good data and a lot of data, it's a huge benefit, okay? For inter-picture prediction, we actually need to predict between pictures to remove temporal redundancy. We use motion estimation, motion compensation. I'm not getting into details of that. What we can do by deploying neural network, we can extrapolate multiple reference frames. We can enhance B prediction. We can, again, learn end-to-end mapping between compensated coding blocks and PUs, right? We can generate even interpolating filters, right? And all that will come currently with a bit rate reduction of something like 4%. It's more difficult to get coding gain here, okay? Because we also need good data for that. So current researches show something like 4, maybe 5, and a little more bit rate reduction compared to HM. In loop filtering, this is very popular, where actually a lot of different researches have been done in this field. Loop filtering actually goes this way. Quantization process, of course, leads to loss of information, okay? And when the loss is too high, we have visual artifacts. So in loop filter, what it does is actually, it tries to remove these artifacts, okay? And to improve visual quality. This is the whole idea here. And what we can do with deep neural network, we can lower the distortion features for inter-prediction coding. We can adapt, actually, to decoded frame, okay, with different qualities. And we can actually learn nonlinear mapping between the distorted frames and corresponding original frames. And as a result, we can get some nice gains, about 10%. This is quite impressive, I would say, okay? Transform, this is an interesting case. So, as you know, most of the codecs use discrete cosine transform, also sometimes Hadamard transform, discrete sine transform, and so on. What we can do with deep neural network, we can fully replace the transform, okay? We can fully replace the transform and get better compression efficiencies than DCT, for example, right? Gain here is currently up something like 9%. The next one is entropy coding. Here, as you know, the entropy coding highly depends on the accurate probability estimation, so we can improve that. We can actually estimate probability distribution of quantized transform coefficient and get again something like 2%. So gain here is a little lower. It's difficult to get gain more than that. Cross-component prediction. As you know, YUV plane still have some dependencies. What we normally do, we define some kind of linear regression model and predict them. So we can also use for this purpose DNNs for extracting features, okay, from the reconstructed Luma samples and using these features for predicting chroma samples in the current block. Okay, the gain here is quite low. Savings here are not supposed to be high anyway. Now, an additional approach is upsampling, downsampling. As you well know, we can actually, because there is a need for many different resolutions, one of the approaches to improve the coding efficiency is to downsample the video, the resolution prior to encoding, and then upsample it back. And it can be done by deploying deep neural networks, and we can use them for upsampling Luma and chroma components in quite accurate manner and get very nice gains, something up to 15% currently, okay? This is really nice. So this can also be done by neural networks. Okay, and the last one, we have a coding optimization. We have, as you know, a desire, we need to assign different coding blocks with optimal coding modes. And also for that, we need to, we can use deep neural networks, okay? We can actually learn the optimal CPU partitioning for the entire CTU, okay? Also apply some kind of early terminations and reduce by such a way complexity up to 50%, which is really significant. So in this particular scheme, we are targeting reducing complexity, simplifying the process, and not enhancing quality, okay? So this 50% reduction comes with some kind of small increase in BD rate. And also we can implement it for encoder control. As you know, we need to do accurate frame bit allocation on the frame level, also on CTU level, and especially it should be allocated wisely for the intra-frames because they consume a lot of bits, and the quality of intra-frames has a direct impact on coding efficiency. So this is very important. It can be also done with deep neural networks, okay? And as a result, we can get much more stable rate control, okay? With a reduced error of allocated bits, okay? So we actually overviewed all different techniques, and let's summarize. So DNNs, video coding parameters obtained based on real and practical data. And again, this is a huge benefit. We don't have formulas here, we don't have algorithms, we have real data. The more data we have, the better the prediction is, okay? We are not limited to some particular pixels, features, etc. We can use everything that we want, okay? And today, as you know, many object recognition, for example, image recognition is done by machines, so DNNs are suited for this very well. So they are both suitable for human recognition and machine analysis because they are optimized, can be optimized both for check textures and fine details and features. And this is a big benefit. Of course, we have significant memory requirements. We have a lot of computational costs. As I said, some particular cases, we have thousands of time increase in the decoding processing time, and we're still not at the point when we can say, yeah, really, we can start deploying them tomorrow. And one more thing, like if we would like to increase the accuracy, we need to use neural networks with more layers. So as you can seen before, we had already networks with 200 layers. So theoretically, we can get more layers. It doesn't mean that the more layers we have, the more accurate the networks became. It's not always the case, but generally it helps, okay? And finally, we can use several deep neural networks to be switched for specific content, okay? So-called content adaptive coding, okay? Now, we come to some interesting part. Look at the pictures of these people and say, what, in your opinion, can be special about these photos? Yeah, okay, you're probably, yeah. So look at these photos, photorealistic, they're really, really impressive, and all these people do not exist. These photos are fake, let's say so, okay? And this is really impressive. Huh? They're fake. So this is really impressive, like how we can actually do that with deep neural networks. Like it's amazing, right? So let's take a look how exactly it's done. I have a short video showing this. Okay, this is also representation of people who do not exist. Okay, so for training, something like 30,000 images of celebrities have been used. So you need a lot of data to get good results. Okay, so those of you who will be working with neural network deployment, get a lot of data. The more data you have, the better are the results. Okay, so by training a database with a huge amount of real photos, it was possible to generate entirely new images. Okay, and that actually mimics the appearance of real photos, and it's really impressive. Now we will see some short representation of how it's done. It starts from low resolution images 4x4, and gradually you increase the resolution. Okay, you generate new photos, new images of people who really do not exist. Of course, the training takes time. So this research was done 1 year ago. So you need something like 1 day to run it on quite strong GPUs. Today you have clusters, huge clusters of GPU. For example, NVIDIA has something like cluster of 1,500 GPU, maybe more. Now, after training, the generator actually maps random number to an image and performs interpolation between images by interpolating the numbers. Okay? And as a result, you get completely new, very beautiful images and photos of fake human. Okay? Now, what is interesting to note is that actually you can do it for every object. You don't need to do this just for photos, right? You can do it for everything, for every object. So think about what can be in the future. Like think 5 years ahead, 10 years ahead, what can happen if you can actually fake everything, okay? And I'm not talking just about the fake of lip movements, you know, just putting the words that some person didn't say. I'm talking about generating videos and photos of everything and faking everything, okay? It's really impressive. So I just will go forward because, yeah, this is the point that I came to. Think like something like 10 years from now. Maybe you will be sitting at your homes and just generating movies, yeah? You don't need to go to some kind of a store and buy a camera. You can sit in your home and do whatever you want. Okay, here you can see some kind of nice representation of what can be done with any object, not necessarily the faces, okay? So just a second, so let's take a look here. Okay, I will go to the next slide. I cannot fast forward this. Now, so what is next, in your opinion? As I said, we can generate fully fake videos and not just changing clip movements. And when, in your opinion, it can happen? Any ideas? How many years from now? What are the estimations? Huh? It started to happen like today. You have really just trials of short videos predicting the next frames. I would not say that it's really happening, but it's starting to happen. I would say in 2-3 years from now, we will have already real, like you will have sequences, video sequences. In these cases, you will not be able to say if it's real or not, okay? Because now it's still not perfect. We are still not there. So if you go forward 5, I don't think 5, let's say 10 years, I am pretty sure that we will be able to sit at our homes and just generate new movies without the need to buy and purchase a camera, okay? Of course, it will not substitute the celebrities, the known actors, but theoretically we can generate them, okay? Okay, thank you.
Thank you, Dan. We also have 65 seconds, I think. Let me go to a different row. I got to share the love for questions here. I'll be geometric. We'll just start in the front and work our way to the left and back.
Okay, yeah, very interesting. All the impact on the different parts of a video codec.
Yeah.
So where was the percent of bitrate reduction taken from? For example, for intra-prediction and.
For intra-prediction, what actually the reason is that instead of using as a reference, it's just the top and left.
No, I mean, what is the work? So do you have a reference for that? It was interesting to.
Yeah, I have, of course. In my presentation, it will be spread. I have references to this.
Oh, okay.
Okay, of course.
Okay, one more question, and then we're going to go to the next speaker.
For something like intra-prediction, to train the neural network, do you use labeled blocks from humans, or
from what?
From humans, subjectively labeled data? Or
it doesn't have to be like it's preferably should be like some kind of, yeah. Look, today the automatic labeling doesn't work perfectly. So normally you do an automatic labeling and then you do human supervision. It doesn't work perfectly by, in automatic manner. You need to do it at some point by humans.
So on a block by block basis, you would have humans say which block.
It doesn't done for everything, but normally you have automatic system, but at some point you need to also to control the process. You cannot control everything. It's not possible. It's thousands of training data. It's not possible. But today, automatic systems work pretty well. Okay.
Thank you very much, Dan.